I want to pick up my discussion with quality improvement. In our last discussion, we talked about how we want to try to produce products that meet the needs of the customers. And I use the example of the pen cap, where we want the diameter of this pen cap to fit the pen. And so the tolerance, or how wide or narrow that pen cap can be, makes a difference. We also talked about what it meant to be quality. We talked about different characteristics of quality in terms of performance, reliability, serviceability. We talked about it in the context maybe of an automobile. And what we talked about is having some processes where we're creating a product. And I mentioned that I built some cutting boards. Here's an example of a cutting board. It started with 3 different pieces of wood. It started with a piece of maple, which is this lighter color on the outside, a piece of cherry, and a piece of walnut, which is this darker brown. And they were just sticks. They were 1 by 6 by 8 feet long, 1 inch by 6 inches by 8 feet long, and then you cut and shape. And each time I do a step, that's called a process. We think of it as a process. And when I do all the processes necessary at the end of the day, I make, I hope, what is considered a beautiful cutting board that, in this case, my wonderful wife Rachel will get to enjoy. So the system, the way that we do it, what we're doing along the way is measuring. And so what we've talked about is control charts. And this is kind of the slide that we ended on last time. We're going to be measuring some characteristics. Maybe it's the amount of glue I use on each of the cutting boards, and I'm keeping track of the amount of glue that's used from one cutting board to the next, and I'm measuring it. And so we create what's called a runs chart. And a runs chart is nothing more than a scatter plot of some data. In this case, it was the weight of the different cereal boxes that I was sampled over 20 days. And this is what you get. Control limits on the top and bottom, upper and lower control limits, a center line here in the middle. We connect the dots, and those are called run charts. All right, now we want to talk about variation. Statistical control is going to be when the distribution of output of that process does not change over time. Okay, in that last picture, let me just kind of go back to it. There's variation. We see that not all the points are the same. When we go down the 2-liter soda aisle, we see different amounts of soda in the bottles. There's variation happens. But is that variation just due to the natural variation of a distribution, or is it because of some other thing? So a process whose distribution does not change, we say that it is in control. There's two phrases. I thought I went too far there. If the distribution stays constant over time, we say the process is in control, a phrase you need to know. If it changes, we say it's out of control. We're talking about the distribution. We're not talking about the output itself. I know, and let's go back and think about some things we've talked about this semester. I know that if an observation comes from, say, a normal distribution, I know that the individual observations are going to vary from within that distribution, right? You're not going to get the same output every single time. You're not going to get the same observation every single time. I know that the output themselves will vary, but the underlying distribution stays the same. And so even though I may see a different amount of soda in a 2-liter bottle, even though I may use a slightly different amount of glue on a cutting board, even though I may have different amounts of soda in the bottle, I might have used that already, even though the individual observations may change, they may come from the same distribution. And what statistical control is talking about is the distribution itself. If the distribution stays the same, then we say our process is in control. If the distribution changes, it's out of control. Now, there's a couple different ways that distributions can change. First, the mean can change. And actually, I wish I'd have given you a picture. This isn't the one. This is from the textbook, but I wish I'd have given you a picture where maybe the means, rather than sliding up, you can see they're getting higher over time. I wish you can think about means decreasing over time, because there's a really good example of when that happens. If you think about the example I used with the cough syrup, the Vicks 44 cough syrup, the bottles, and they look something like, this is going to be a really bad picture of a bottle, by the way. That's not terrible. The bottles look like this. We're filling them with cough syrup. Well, the machine that fills them has some kind of nozzle that eventually gets placed over the bottles and fills up the bottles. Well, over time, the nozzle gets a little bit of residue of cough syrup on it, and it builds up. Occasionally these things need to be wiped down, because if the nozzle isn't wiped down, you get a blockage. You get to where the cough syrup doesn't flow through smoothly or cleanly, and what happens is over time the amount of cough syrup, maybe it should be up here, but over time with this blockage here, you get a little bit less, and then you get a little bit less, and you get a little bit less. And eventually, hopefully before you're looking at a bottle that's like down here with cough syrup, hopefully someone says, hey, wait a second, we have a problem. We've got to wipe off this nozzle, clean it up. And in that case, what would happen is you may start with a distribution right here. And what we're saying is at time period 1, what these curves are representing is the observation we get is going to come from that distribution. At time period 2, maybe that distribution slid down a little bit because the nozzle has a little bit of residue. At time period 3, it slid down a little bit more. And then I can actually use time period 4, time period 5. And you can see that there's a trend that's going downhill. We want to see perfect across the board distribution staying at the same spot every time. And so in this case, the mean, the picture that I started with, the mean was increasing, but the picture I'm drawing here, the mean is decreasing. Give you a good example of why that happens or how that could happen. And so that would be the process changing because the mean's changing. Another example is that the variance is changing. In this case, you can see that the mean is located, if I can draw a horizontal line here or something close to it, the mean is pretty consistent across the board, but obviously from time period 1, 2, 3, 4, and 5, it's getting more spread out. So the distribution that we're observing changes. You can see how in distribution 5, you're going to get wild swings of observations. If you're pulling a piece of data from this distribution, it's going to be crazy. Now think about that control chart. Think about that upper, that lower control limit. Can you see how in time period 1 we're going to see something scattered real close to the line here, but in time period 5 all of a sudden we're going to get observations all over the place. In fact, we're going to get observations that fall outside the control limits. So the variation can change. And the worst case scenario is here where everything changes. The mean, the standard deviation, they both change. And so this is crazy when this happens. You can see both the mean and the variation are changing over time. You don't know what's going on. The center's changing, the variation's changing, it's getting bigger, it's getting smaller, it's going this way, it's going that way. That's a mess. Any of these situations where you have the distribution that's changing, that's called out of control. What we'd like to see is the mean and the variation staying consistent over time. Now the book didn't have a good picture, so I tried to draw what that would look like. And so what you see here, what I tried to show here, is that the mean is staying the same, and if I could have, I would have drawn the same curve over and over and over again where the variation was staying the same. And really I think what we're seeing is, I can't draw all that well, but hopefully you get the idea. The distribution staying the same. So the observations, and you can think about the control limits might be, that might be the upper control limit, the 3 standard deviations, and that might be your lower control limit. Again, the formulas for the control limits aren't necessarily standard deviations, but if you think about them that way, you usually have pretty good success. And so that's what statistical control is. This would be in control because the distribution is staying the same. The prior 3 examples, mean changing, variation changing, both changing, out of control. All right, definitions you need to know. There are 2 types of variation. There's common cause, and this is the variation that's inherent to the process. You can't change it, you can't remove it, you can't alter it, you can't do anything. That's just this is sometimes I call it the deal with it variation. This is the variation that's caused by the distribution you're working with. That's all you're capable of. You can't get any better than common cause variation unless you go back and reconfigure the system, start over, do something different, build a better machine, change the people, do something different. Because if you're just looking at common cause variation, you're saying, well, we need to reduce this without making any changes, you're just going to bang your head on the wall because you can't. Now, there's another type of variation called assignable cause or special cause, and unfortunately we use both those names kind of interchangeably, not one or the other. You can use either. Assignable or special cause variation, and this is caused by things that you can fix. This is caused by rogue people. This is caused by machines, materials, environment. What were those 6? I missed a couple of them. Let me go back in your notes here. Material, methods, measurement, environment, people, machine. Those are the 6 sources of variation, and sometimes they do things outside the system. We didn't design it this way, but it's happening now, and those are called assignable cause or special cause variations. hopefully the control charts are used to help us distinguish between these two types of variation. We're going to look at the charts to try to figure out what's going on. Is it common cause? Is it just same old, same old? That's the variation we have to deal with? Or is there a reason we're seeing points like this? Or is there a reason why, this is pretty funny, 1 year, years ago, this is a long time ago, gosh, I can barely even remember this, but I remember, I don't remember the circumstances around it. I do remember I had just mowed the lawn. It was in the summer. I was hot. I was sweaty. I was just wanting an adult beverage. And I reached into my refrigerator, and there was one adult beverage left. There was one can of beer left, and it was a can. I don't know why it was a can. I'm a bottle guy. Anyhow, I reach in, and I pull out the last can, and it was a 12-pack that was in the fridge, and it was at the very back of the box because it was the last one. I reached in and I pulled it out, and it was completely empty. I mean, there was not a drop of beer in it. It was completely empty, and I was completely disappointed, but at the same time, as disappointed as hot and sweaty and tired, and I just wanted to drink that beer. At the same time, I was thinking, this is going to be great for a conversation of variation because this shouldn't have happened. Now I know when I get a 12-ounce beer, there's 12.2 ounces, 11.8 ounces. There's variation that I can expect and that I can deal with, but to have none? Back in the day, my kids were too young. Otherwise, I'd have thought, hey, what are you guys doing? It wasn't anybody going in there. It was completely sealed can with absolutely no beer in it. That was because of an assignable cause of variation. It's not a common thing. In fact, I've never seen another can like that. Completely sealed with absolutely no beer in it or no soda in it. I've never seen that in any other situation at all. Somebody messed up. Now, of course, being the statistician, knowing that I talk about quality improvement, I said, this is an opportunity. I'll be able to talk about this in class. At that moment, however, I was a little bummed out. And so control charts are hopefully going to help us distinguish between these two types of variation, and hopefully get us to the point where we can identify there's a problem before we start shipping empty beer cans out to our customers, because that's not going to fly. It may happen occasionally, once in a lifetime. You laugh about it, you shrug it off. But if I routinely had empty beer cans in my 12-packs, I'm going to stop buying that kind of beer. Let's face it, I'm not going to go there anymore. So anyway, let's talk about some control charts. Different types of charts. The different types of charts, as you might have figured out, are going to be based on the different types of things we're measuring. Sometimes we measure quantitative data. Sometimes we measure qualitative data. We've talked about means and proportions this semester. Well, we have similar things here. I'm going to put these two together. These are a team. When we're working with quantitative data, usually we're taking samples. And again, the sample sizes, usually you're sampling 5 or 10, very small sample sizes. And we think of working with the X bar. Before we do that, however, this is usually good to know for you guys. Before we look at means, we look at what's called the R chart, the range chart. We look at that one first. And the range, again, back in the day when this stuff had its start, ranges were used as opposed to standard deviations or variances because ranges were easy to calculate. If someone gave you 5 numbers and they asked you to calculate a standard deviation, you may stand there scratching your head, especially if you don't have a computer or a calculator to work with. You got to do it by hand, which is how it was done back in the day. But if they asked you to calculate the range, you just look at the extremes, the biggest and the smallest, and you subtract them. And so ranges were used. And so there's an R chart. We're going to look at that because that's our look at variation. We're going to look at that one first. And then if that one is okay, we're going to say if that one's in control, then we'll look at the X bar chart. But the order is important. We want to look at the X bar chart first. You look at the R chart, get that one set to where it's working okay, and then you look at the X bar, and I'll talk more about working okay in a second. There is an S chart, which could be used in place of the R chart, but pretty much R and X bar charts are what are still used. If you're working with just individual values, you can't take a look at a mean or a standard deviation or a range of an individual value. So if you just sample one, there's an X chart. But again, it's for quantitative data. If you're working with qualitative data, you look at a P chart, percentage. Percent effective is typically what you're working with. Percent right, percent wrong, whatever it happens to be, but it's called a P chart. And so we're using a lot of the same symbols, X bar for quantitative, P for qualitative. It's just the X bar has to get teamed with the R before you look at it. And so there's different types of charts. Now, working with control charts. This is going to seem maybe a little silly or a little or difficult. I don't know what the right word is. But just hear me out, and then we'll see how relatively straightforward this process is going to be. First, you're going to collect data using a rational subgroup strategy. This is a tricky one. Data collected within a sample have a good chance of being similar. Data collected from different samples have the greatest chance of being different. Now, what the heck does that mean? All right. When I worked with the cough syrup, let's go back to that example. I mentioned how the lab coats, the scientists, the quality improvement folks, they came into our little horseshoe, our little production line about once an hour, and they would take bottles. And they would take them away and they would measure them. And if we're talking about a qualitative measure, they would say if it has a label or not, yes or no. Maybe they'd sample 10 bottles and they'd see that all of them had labels. Maybe over the course of the day they'd sample 100 bottles and they would see that all of them had labels, or maybe one didn't have a label, or maybe one label was incorrect. But you're talking about a P chart there. They're measuring the bottles to see how much cough syrup they have in them. And so they're getting an X bar. Maybe they sample 5 bottles and they find that the average cough syrup is 8.02 fluid ounces in an 8-ounce bottle. And so they're taking measurements every hour, on the hour, on the hour, on the hour. And the goal is when they came in, they would sit in the middle of that U-shaped production line, and they would kind of look at their watch and be, all right, it's time. And as soon as they said it was time, they would go and they'd very quickly take bottles off the line and put them in the cart, and then they'd get out of there. And the goal was they would try to get data within that sample to give you a really good snapshot of what's going on at that particular moment. And so the bottles they were pulling off the line should look all alike. They should come from the same distribution because they were taken at the same time. And so the data collected within a sample, we want them to be as similar as possible. But when they came back an hour later, and then an hour after that, an hour after that, it gave it an opportunity for the distributions to change. Data collected from different samples have the greatest chance of being different. Now, the key idea here is we don't want there to be any chance of them being different. We don't want things to happen. We don't want assignable or special causes of variation to come in and have an effect on whatever it is we're dealing with. But if it is going to happen, if something's going to go wrong, if people mess up, if machines are going to break, if material's bad, if the environment changes, if the way we measure, if any of those sources of variation are going to creep in and wreak havoc with our process, with our system, we want to be able to find it. And so we sample so that when we take those samples, there's a good chance. If differences are going to happen, we've spaced it out enough so that we can find it. Now, it's a little tricky because the question everyone always asks is how often do you need to sample? And that's a toughie because it depends upon what you're doing. Every process is different. And so usually what people will say is let's sample frequently, more frequently than you want. Let's sample every hour. And maybe even start every half hour. Let's sample every half hour. And then when you start seeing that there's no difference between one sample and the next, you start saying, well, gosh, we keep sampling, we don't see any difference. Well, then you go to an hour. And then you go to 2 hours and 4 hours. And eventually you're like, well, we waited too long. We went in 4 hours and we saw a change after 2 hours. All right, well, let's bump it down to 2 hours. It's kind of a trial and error type of how often do we need to sample. But these are the two strategies, or these are the two ideas within this strategy that you need to consider. I want to be able to detect differences, but I don't want the difference. I want to detect a difference right after it happens. That's really the idea. And unfortunately, we don't know when that'll be. I want something to go wrong and meet a sample at the very next possible moment. I don't want to sample just before something goes wrong, but because when we don't know when things are going to go wrong, that's kind of tricky. And so that's the idea. We're going to collect data. We're going to create the control charts, the P chart if we're working with qualitative data, the X bar and the R chart if we're working with quantitative data for the data collected. And then this is the part I need to talk about next. We're going to conduct what's called a pattern analysis. Sounds kind of daunting, like, ooh, what does that mean? The way we look at it is going to be really easy. To identify special causes of variation. If nothing's going wrong, there won't be patterns. It'll just be random noise. It'll be random variation that's bouncing around within the control limits. If you see some kind of pattern in your data, that's going to indicate that things are going bad. And hopefully, by looking for these patterns, we can catch something going bad before it gets too bad. Hopefully we can catch a problem before you end up with an empty beer can. Hopefully we can see that the nozzle hasn't been blocked It's just getting a little clogged. So we're getting a little bit less and less beer before all of a sudden you open a can and there's nothing in there. So we're going to conduct a pattern analysis. Let's talk about that. Pattern analysis. Wow, look at this. This looks like a mess. All right, let me break it down for you. And you'll see that it's not terrible. If we think about, let me go to this upper left one here. If we think about it, here's our, and you can think about a bigger picture here. Split, bring these axes down. Okay, this is the time down here on the x-axis, and this is whatever it is we're measuring. There's an average, there's a center line, which I'll put here, and there's the control limits. Now remember how I talked about, and these plots really make it work well. Remember how I talked about the control limits? Think about them as 3 standard deviation lines, right? I said that's not really how the formulas look, but just think about them that way. Well, what this is saying is, if you think about it, there's 1, 2, and I guess I should start here. 1, 2, 3 standard deviations above the mean. 1, 2, 3 standard deviations below the mean. And if I was to draw a picture, we know if we have a normal distribution, and if you think about that curve being right here, we know that's what to, we know that 68% of the observations fall within 1 standard deviation of the center line. We know about 95% fall within 2 standard deviations, or plus or minus 1.96 for those of you in the know. And we know approximately all fall within 3 standard deviations. So we know what to expect. And what this is saying is breaking it into zones. The zone, the 1 standard deviation zone, that's the C levels. Between 1 and 2, those are the B levels, and between 2 and 3, those are the A levels. What this is saying is if you see an observation out here beyond the 3rd standard deviation, beyond zone A, that's a problem. Something's wrong. That indicates that something is wrong. You have an assignable or special cause of variation that's causing this. Find it. Look at the one, rule 2 here. We know if we had a nice normal curve, I'm going to draw it here over this. If we had a nice normal curve here, we know, whoops, that's the idea was to draw a nice normal curve, not some mountain peak, sorry about that. But we know that half of the observations should fall below the mean, half should fall above the mean. So if we're going to randomly sample, it's going to bop around. Now, could we see 2 observations in a row on one side or 3 observations? Yeah. What this is saying is, if we're choosing the same distribution, we shouldn't see 9 in a row. We shouldn't see 9 in a row on either side. If we see 9 in a row on either side, probably what that's indicating is our distribution isn't centered at the center line. Our distribution's probably somewhere more like this, where this is the new center line. You see some above it. It probably means our distribution is shifting. The mean's changing. We got an assignable or special cause of variation. Something's wrong. Clean the nozzle. Do something. But you got to check to see what's going on, because this isn't the common cause variation. This isn't just expected variation. This is a problem. And that's what all these rules do. Rule 3, 6 points in a row steadily increasing or decreasing. If they're just going up or just going down, doesn't matter where they're at. Again, it's probably the mean changing. 14 points in a row alternating up and down. Looks kind of good. It's not. Not if they're going back and forth. Something's wrong. 2 out of 3 points in zone A or beyond. 4 out of 5 in zone B or beyond. There are different ways of looking for patterns. Now, here's the problem I have. These patterns, while they work, and it's, obviously they're published here, they work, they indicate a problem. They're not the only ones. Some people use 10 points in a row. Others use 8. 6 points in a row steadily increasing or decreasing. 14. They're not, those numbers aren't in stone. Depending what textbook you go to, depending what software you use, you're going to see different rules used. And so this becomes a problem for me, because I have to ask you to work with this. It's also a pain in the neck to remember. So here's what I'm going to do. I'm going to make it really easy. This is the rule. This is what you're going to look for me. I'm only going to have you deal with rule number 1. It's going to be really, really simple. So here's how you're going to work with control charts. You're going to conduct a pattern analysis of the charts to identify special causes of variation in the data. You're only responsible for that first rule. You'll see a couple examples in a second. I'm going to give you some charts to look for or look at. You're only responsible for that. If you identify a special cause of variation, you need to go, or if you identify a problem on a plot, it's because of a special cause of variation, go find it. Whatever it is, whatever the process is, whatever you're dealing with. If the pen caps are all too big and they don't fit on the pen caps anymore, you got to do something. You got to fix it. And so you go and look for it. You go investigate the cause of that variation, and you go and remove it. And then you continue. And it's a never-ending process. Once you begin the control charting, you're going to do it forever because you're always going to be analyzing the data, seeing what the data says. Is there a problem on the horizon? Did we see something? It's actually an interesting process once you get into it. All right, so let's take a look at a couple examples. Here's an example where I took some samples and I'm looking at R charts and X bar charts. And these are the control charts that are generated using our software program. And what I want you to do is to identify if rule number 1 is broken. And what that really means, and you guys are going to be happy with this, is at the top of the graph we see our upper control limit up here. We see our lower control limit. Are there any points outside those limits? No. We're going to look at the R chart first. Remember, this process is in control. I shouldn't say this process. This chart is in control. Before we say the process, because the R chart's in control, now we look at the X bar chart. I want you to do the same thing. Upper, lower. Are all the points between them? You bet they are. This chart is also in control because both these charts are in control. We're going to say the process is in control. And that's it. That's how we use control charts. Everything's good. Now let's take a look at another one, a P chart. And you can see here, upper control limit, lower control limit. That's a problem. That's a problem. You look at this guy here. Ooh. Is that a problem? Is that outside or is that right on the line? Tough call. Well, the reason I'm having you work with just rule number 1 is because if any of the other rules are broken, the computer's going to tell you. It's going to say, hey, look, observation 3, 7, 9. We got problems there. We got what this program says that we have exceptions at 3, 7, and 9. Warning. Case 10's right on the line. What's this? Like case, what is that, 27? Is right on the line. They're fine. It's not important that you memorize those rules because the computer's going to look for them. Now, our software doesn't use exactly the same rules that are listed in that previous slide in the text. It has different rules. So I don't care so much about the individual rules. I want you to have a general idea of what quality improvement's looking for. We're trying to figure out when things are going wrong. Something's gone wrong in this process. If things weren't going wrong, all the observations should be within the control limits. None of those patterns should be observed. And we're seeing it. 1, 2, 3. Something's going on. We need to go to observation 3, 7, 9. We got to take a look at why were they what they were. Let's investigate a little further. And usually if you know about your processes, you know what's going on, you can pinpoint. Is it a person? It's the same person on the job here? Because someone may need to be retrained or talked to. Is it a machine? Is it the material that we used? What's going on? Something's causing these changes. We need to figure it out. Because if we can figure it out, our process is going to get better. And one of the things that happens when you do these control charts, as you start figuring out your processes, because these are your outliers, these are your extremes, our spread here is greater than it normally should be. And so once you get rid of the extreme values, once you fix that problem, all of a sudden these control limits start to pinch in. You start to get better results. And when you get better results, you start to understand your process better. And it just leads to improving your quality. It's kind of the point, right? Quality improvement, methods of quality improvement. We're looking at a couple simple charts, a couple simple ideas, variation. Now along the way we've run into some terms. 6 sources of variation, dimensions of quality, the assignable cause, special cause, or common cause variation, two different types of variation, the different charts. So there's some things to look at, but here's my promise to you. All the material I want you to know with quality improvement, it's in these videos, it's in these slides. So there's no need to go out for any outside source of information. Take a look at this material, and hopefully it makes a little bit of sense to you. Quality improvement, looking at some scatter plots, some advanced scatter plots of some data, and learning some information about what it is we do. That's our goal. All right, so hopefully you have a little bit of an understanding of methods of quality improvement. That's all I really want to do with it. It's the last material that I'm going to cover with the quality improvement, so hopefully it makes sense. If not, you know how to get your questions asked. So hopefully you'll have a good day. I'll talk to you later.